Today we're going to talk about the system with damping included. So the classes that you had before, there wasn't any damping. So today's class will be that added damping. So if you recall, we have this kind of sketch before. So what I'm going to do is add that damper. So if we were to consider damping, and we have seen it before, the damping force F is directly proportional. So this is directly proportional. Directly proportional to the velocity, or x dot. That's the velocity. So if you remove that proportionality, then that damping force F is equal to C x dot. Right, so you have seen that before in the first lesson. So this C will be our damping coefficient. And if it's linear coefficient, that means the units is newtons seconds per meter. For rotating system, and later on there'll be an example to show you a rotary system. The units for that will be newtons meters seconds per radian. So this for a translational system, the units for damping coefficient. This is for rotating system, the damping units will be given by this. Okay. So today we're going to talk about damped system. So it's not undamped over here. This will be damped. Okay. So I'm going to sketch the damper. If I were to add a damper in here, it's going to look something like that. It's going to look something like that. I don't know why you're So if I were to have it over here, attach it to a mass, then the mass is going to pull it down a little. So this part here is going to get pulled down, right, the lower part. So maybe I noticed that some of you don't really know how a damper works. So this part here is one piece. This part here is another piece. Okay. So you can move this thing upward. So then it slides along the cylinder and it becomes better. That's how the damper works. So what I've sketched over here is for the static condition. If you look at the disturbed condition, then you're going to pull down that damper together with a spring. So probably it's going to look something like that. Right. So what I've sketched is that this kind of space that's in there will be increasing. It's not really sketched to scale, but you get the essence of it as you have the dynamics or the disturbed condition, and the damper will be pulled down. The damping coefficient, C, will be the same for all these various cases. And that amount that has been displaced, we were saying that is equal to x naught. We used to call it the dynamic deflection, but it has a maximum value as you pull it down, and you release it, and then you oscillate. So let's have a look at the free body diagram and the free body diagram. So in order to sketch a free body diagram, we need to cut these two ends if we were to do that, we saw that for the spring, it's going to look like that because the spring will be under tension. So if it's under tension, then I sketch that way to show that the spring is under tension. We pull it. And there will be an equal and opposite force in that way. If I were to cut the damper, this is what's going to happen. So damper will cut. In that way. So for a static condition, so I'm going to write down. For the static condition, there is no force. Right. I'm going to underline that. Acting on the damper. So that means this forces over here, F, due to the damping, F will be equal to 0 for all of them. That's for the static condition. Why is that so? Because the damper, if you don't move it, then it doesn't provide any damping force. That's unlike spring. Spring, you gotta compress it and stay there. You still get that spring force. For damper, you gotta compress it and stay there. Then you wouldn't find there's any more force. It's only when you are pressing it, in the process of pressing it. So for the disturbed condition, this is what you're gonna have. Because it's being disturbed, that means being moved. So if I were to break that link in order to find a free body diagram, then I'm gonna get the respective forces due to the damping. So in this case, the damper would be under tension as well. So equal and opposite force. And the force that's over there, the damping force, F, will be equal to C x dot. That's the damping force. The spring force, you have seen before, that was in the last week. In the last week, that spring force, in this case, F, is equal to K delta static plus X. Right? That's your spring force. So we're gonna sum them together today. So there will be these four damping forces. So in order to help you to visualize, what I have is the small little model. So what I have over here, is this Lego pieces, and this one has got a spring that's embedded in it. So if I were to press, I can feel, you can see my finger over here, right? There's constant force acting on it, on my finger, and if I were to release, it will come back. So I bought two, and I took out the spring. So again, the spring, if you were to press on it, then you can see that there's forces that's acting on it, on my finger. Right? No matter at which state of compression, there's always a force that's acting on it. But for the damper, it's a bit different. The damper, if you notice my finger over here, if I were to press on it, you can see that it moves, and then there's a force that's acting on it. Once I stop, there's no force that's acting on my finger. So what that means is that this is the case of static condition. When I stop, there's no force acting on it, and in order to experience this damping force, I need to have constant movement. That constant movement comes about because of the dynamic condition that we're talking about. That it is moving. So Please take note of these differences. So always remember, in static condition there's no force from the damper, but there's force from the spring. In the disturbed condition, there's forces that's coming in both from the spring and the damper. So let's build up the equation of motion. Let's start with the static condition. So for the static condition, we'll sum up the forces, Fx, and then that must be equal to 0. What kind of forces? We're interested in this area. Considering the mass, right, for the static condition. So sum up all the forces. What you have is mg, that's in our convention direction, so it's positive value. And that spring force F is equal to K delta. I'm going to stop writing that static ST subscript now. So minus K delta equal to 0, right? The two forces. And that spring force is acting upward, so it's against our convention, so there's a minus sign. Let's consider for the other one, the dynamic condition. Also considering around the mass. So this is the one that we're interested in. And the force for that spring, F, is equal to K delta plus X. Right? So do the same thing, summing up the forces in the direction of X, and sum that because dynamic condition, so it's equal to mass times acceleration. So mg is in the direction of our convention, it's positive value, minus force that's due to the spring in the opposite direction, so minus K sigma delta plus X. And there's another force, there's a spring force, so I'll use the red color. And that damping force is in the opposite direction, so minus C x dot. So equal to M x dot dot. So let's break out that bracket. Mg minus K delta minus Kx minus Cx dot equal to Mx dot dot. So this term over here, we can see from the static condition, this is equal to 0. So let me readjust a little bit. There's Mx dot dot plus Cx dot plus Kx equal to 0. So this equation over here, this is what we call the damped second order system. And it is the most basic form of a second order system with damping. So the case that we had last week, it was without a damper. So now what I've done is to add a damper. So that's why we have this term that's coming in. If you remember last week, there wasn't this term. Last week it was Mx dot dot plus Kx equal to 0. So now we have the damper, so that's that term. So we can simplify this by dividing it throughout by M. So I have C divided by M, x dot plus K over M, x equal to 0. I'm going to call this equation 1. Now we have seen before the undamped natural frequency. The undamped natural frequency, omega m, that's equal to square root k over m. That was seen last week. Right? This week, I'm going to introduce to you a new term. Introducing damping ratio. So damping ratio is different from damping coefficient. So please do not mix up with these two. Damping coefficient, that's C, the C value. Damping ratio is this symbol over here. Correct? This symbol is called zeta. Zeta or zeta. Some of you learn in different ways. Note this symbol in your set of lecture notes in printed form. It's kind of like written in that way. Zeta. So in handwritten form, I just write it in that way. Do not mix up this with another similar looking symbol. That one.
Whoa.
What? That's called xi. Xi in Greek. Xi.
Chinese and Greek are different.
Please do not mix up xi with another Greek symbol that looks something like that. Right? Okay, I'll write it better. This one is called no, it's pronounced Greek as chi. And this one probably you've seen before. This one is psi. Okay. So we are not interested in this. We're interested in this one. That's zeta. So don't mix up with all your Greek symbols. So this damping ratio, for now, I'll introduce it in the following equation. C over 2 square root k m. Right? Why is it in this form? Well, actually, if you do the units, if you put in all the units, you'll find that this is dimensionless. This damping ratio is dimensionless. It's going to tell us a property later on, right? So for now, this is definition. And I can re-express this with C as a subject. So C equal to 2 zeta square root km. Right? Later on, I'll make use of this relationship. How this came about? Well, somebody was smart enough to put them together in this following way because they are dimensionless. Yeah? And why divide by 2? That's a certain purpose that you'll get to see later on. So, this term over here we have seen before. For a second order system, this term C over M is actually equal to if I were to put this 2 zeta square root km or C and then divide it by M. So I need to simplify this term. Right? And the way to simplify it is that I'll take this M over here, which has a power of 1. M is actually the same as writing it square root of M multiplied by square root of M. Right? you take square root of n multiplied by square root of n to get n. So I'm just going to break it down in that way. And this will be square root kn. Now why I do that? That's because square root of kn is the same as square root k, square root of m. So I can cancel this. So this will become 2 zeta square root k over m. This term square root k over m sounds good to us because isn't that the same as my undamped natural frequency omega n? So I'm going to replace it. 2 zeta omega n. So that's why this center term with the x dot, the coefficient that comes with the x dot, will be equal to 2 zeta omega n, and later on we'll make use of that. So equation 1 now becomes x dot dot plus 2 zeta omega n x dot plus this term over here we have seen in the natural oscillation or the free vibration. This term here is omega n squared x and then equal to 0. I'll call this equation 2. So equation 2 hence now will be our damped second order system. So you have seen this damped second order system. I wrote it over here. Right. So this is in terms of mass, damping coefficient, and spring constant. That can be expressed similarly in this following way. And this is one that you get to see more frequently. Yeah. So if I have this kind of second order differential equation, we always would like to find out what is the x t, right? So that means we need to go about solving it, is trying to find out what is the xt by using a few mathematical tools. Your lecture notes gave you one format, that is using the Euler's approach. I'll give you another approach that is using the Laplace transformation. So you can make a comparison, right? So you get two. And in your exam, you can either use Laplace transformation or the Euler's method. And later on, we'll solve some questions that I will use two methods. And today's class, we're going to pick up speed, so you wouldn't be going that slow. So if you find that it's hard to catch up, catch up. Don't just try to find it hard to catch up, just catch up. Okay? So let's have a look. Free vibration of damped second order system. So remember, we're talking about a damped system, no longer about undamped system. So we need to have these few initial conditions. The initial conditions of when x, that is the displacement together with a spring and damper, at time equal to 0, that displacement is x naught. So you kind of pull it down with the x naught value before you release it. So that's your initial condition. And the other one, that is the velocity at time equal to 0. Just before you release it, that velocity is equal to 0. These are the two initial conditions. If I were to remind you, if I take Laplace, and this symbol over here, that looks like an L, that's a Laplace symbol. If I take Laplace of x dot dot, that's equal to s squared, capital X, f, minus s xx times 0, and minus x naught, x dot at time 0. So this term over here will be talking about our initial condition, and is equal to 0, so I can simplify it. Is s squared xs minus s, and this x at time equal to 0 will be x naught, substituting my initial conditions. If I were to take Laplace of x dot, then that will give me xs minus x at time 0. And how I got this is all coming from your Laplace table. So if you refer to your Laplace table, you'll be able to see these two lines. Together with initial conditions, again, this one can be simplified in the following example. Why do I take Laplace of this x dot dot and x dot? That's because I'm trying to solve this second order differential equation. So now, if I were to take Laplace transformation of this equation 2, taking Laplace transformation of that. So Laplace transformation of x dot dot now becomes this term that I just solved as s squared xs minus s x naught plus 2 zeta omega n. I'm going to keep that. Laplace transformation of x dot, that will give me as xs minus x naught, and then the last term omega n squared xs equals 0. So I have a common factor that I can see, this one, and this one. So I'll take it all out. xs, that will be s squared plus 2 zeta omega n s plus omega n squared. Alright? So if you multiply it in, you'll be able to see that. And bring the rest to the right hand side. So I'll have it simplified in the following way: s plus 2 zeta omega n. Right. So that's x naught for s, and then it's x naught over here, 2 zeta omega n. Right. So I simplify it in that way. So keeping xs as a subject, now I will have x naught, I'll bring it to the front, and then s plus 2 zeta omega n over s squared plus 2 zeta omega n s plus omega n squared. I'll call this equation 3. So whenever we try to get what is this term xt, sometimes we call it the time response. If you want to try to do that, then after taking Laplace, you must be able to take inverse Laplace. But then we can't take an inverse Laplace on this form over here. Why so? That's because if I were to show you your data sheet, in order for you to take inverse Laplace, you must have this kind of form, right? You must have the denominator part, this kind of form. So if you look at this form over here, it doesn't have that kind of format. So if it doesn't have that kind of format, that means we have to somehow make it into that format so that later on we can do an inverse Laplace. Why we need to do inverse Laplace? So that after inversing that Laplace, it will go back into the time domain. Now it's in the S domain, right? So let's see how do we go about making that denominator in those formats. So to obtain xt, which is your time response, we need to factorize equation 3 factorize the denominator. And after we have factorized the denominator, then we take inverse Laplace transform. Yep. So let's focus on this denominator first. This is s squared plus 2 zeta omega n s plus omega n squared. If I were to take this and then do the factorization, right? Do you remember that there is that roots formula? Ax squared plus bx plus c equal to 0. Do you remember if you need to find x, there is this roots formula that is minus b plus minus square root b squared minus 4ac divided by 2. Do you remember this whole frame? Yeah, this whole frame. If you remember this whole frame, that's good because today we're gonna party with this whole frame. So if I apply this quadratic formula, right, this is called quadratic formula, to this form, so that means my s will be equal to minus b, so minus 2 zeta omega n, plus minus square root d squared, so this will become 4 zeta squared omega n squared, minus 4a, this equals 1, and c, that will be omega n squared. Divide by 2a, and a is equal to 1. So I can see that there's a common factor at the bottom here, 2. There's a 2 over here, and there's a square root 4 and 4. So what I'm going to do is take out that square root 4 outside. If I take out square root 4 outside, that will become 2, because square root of 4 is equal to 2. So this, and this will cancel out. So what I'm left, that will be minus zeta omega n plus minus, and there's a common factor as well, omega n squared, I'm going to take out omega n squared and square root. So that will give me omega n. So whatever that's left in the square root, that will be zeta squared minus 1. And denominator is no longer there. So this is equal to, there's a common factor of omega n, I'll take it out, minus zeta plus minus square root, zeta squared minus 1. If you have a root that's in this way, when we put them together, it's going to be a little bit different. So what I mean is that, let's say for example, I'll give some numbers to this. Let's say maybe x squared plus x minus 6 equals 0. So if you use this quadratic formula, you'll find that x will be equal to minus 3 or x is equal to 2. Right? After you factorize it. And in order for you to express it in an equation, so you take this x instead of minus 3 is plus 3, and then x instead of plus 2 is minus 2 equal to 0. So that's how you factorize it. Yep, in your earlier education. So the same thing. Now I have this kind of thing that's kind of like my x term here, equal to this. So if I were to put them together, back together, my xs from equation 3, x naught is still going to be there. The numerator 2 plus 2 zeta omega n is going to be there. Right? If you refer back to your equation 3. equation 3 is here, so I'm just rewriting this. But this part I have already factorized. Right? This part I factorized. So in order to put it into two brackets that multiplies each other, I'm going to make use of this term. So it's going to be s minus omega n minus zeta. And I'm going to use the first one first. That's plus square root zeta squared minus 1. And the other term over here is s minus omega n minus zeta. And instead of plus, over here it's minus. And square root zeta squared minus 1. I'm going to call this equation star. Later on I'll come back to it. So when I talk about equation star, you will know which one I'm referring to. So now that we have this form, this denominator in this form, so given that what we saw before, zeta is equal to c over 2 square root km, right? That was when I was introducing what is zeta. Could you now see that if c is greater than 2 square root km, then what will happen to zeta? It will be greater than 1. Yeah. So if c over here is greater than this denominator, that means your zeta here is greater than 1. I have another case. If c is equal to square root of km, then what happens to zeta? It will be equal to 1. Yeah. Another case, c that's lesser than 2 square root km. Then what happens to zeta? It will be less than 1, yes. So these three cases you have learned before in your earlier education. These two cases over here, where zeta is equal to 1 or greater than 1, these are called real numbers or real values. This one here will be your imaginary number. That is real number. So what I want to sum up is when zeta is greater or equal to 1, that means your omega n, this term over here, is a real number. And if zeta is less than 1, that means your roots is imaginary. So why do I mention this? That's because later on I'm going to depend on these two words. Is it real or is it imaginary? Because later on, the method used to factorize equation 3, right? Method used to factorize equation 3 depends on zeta. What is the value of zeta? So you've seen before, there's going to be 3 cases of zeta. So let's have a look. Case 1. When zeta is less than 1. This case 1, when zeta is less than 1, it has a name. We call it the underdamped system. Note, is not undamped system. Is underdamped, not undamped. undamped was the case when there's no damping, and we discussed that last week. Today is with damping, and out of which damping, if zeta is less than 1, we call it an underdamped system. So what we're going to do next is to re-expressing equation 3 denominator. So if we re-express equation 3's denominator, I'm going to write it up again. That's the denominator, s squared plus 2 zeta omega n s plus omega n squared. If we were to re-express this, I know previously I've already done that factorization job, so later on I'll make use of that. But there's another way to factorize. And the way to factorize depends on if zeta is it greater than 1, lesser than 1, or equal to 1. So this is a case where zeta is less than 1. How do we factorize this? I'll factorize it, break it down into s squared plus 2 zeta omega n s, and I'll add a term to it. I'm going to copy down this plus omega n squared. Right? So I'm going to add a term to it. This term is omega n squared zeta squared. If I were to do that, then I need to minus that same term, omega n squared zeta squared. Why do I add and minus this funny term? Later on, you'll be able to see why. So now I can split it up that way. Now, if I have a term that's in this round bracket this way, this term is actually the same as s plus zeta omega n squared. They are the same. And this term over here, this omega n squared is a common factor. I can bring it up. So I have 1 minus zeta squared left. How this term came to this? Well, you can square it and you'll find that you get back to this term anyway. Right? That's the factorization. So I'll keep this term, s plus zeta omega n squared. And this term over here, I'm going to take the square out of it. That means omega n square root 1 minus zeta squared. I'll take that square out of it. So this term that's in the round bracket, this term over here, without the square, just the one in the round bracket, this is a new term that I call it omega d, where omega d is defined as damped natural frequency, or sometimes it's just damped frequency. Omega d is equal to omega n square root 1 minus zeta squared, that formula. So that can be simplified now as s plus 2 zeta omega n squared plus omega d squared. Right? So this term about omega d is equal to omega n square root 1 minus zeta squared. If you're wondering, do I need to memorize that? Actually, you don't have to, because I've inserted it into your data sheet. That's awesome. Where is it in the data sheet? Let's have a look. I'll come back to this slide. It's right at the front.
The s plus 2 one. Mine only s plus 2 zeta.
You can find it over here. Omega d is equal to omega n 1 minus zeta squared.
You follow me.
So this is in
Now you see the 2.
this equation. So 3, after we factorize it, now it becomes the following expression. Xs equal to x naught s plus 2 zeta omega n.
Sir, that s plus 2 zeta, actually the 2 is not needed, right? Yeah, there's a 2 there.
There shouldn't be a 2 here, right?
Okay.
Thank you.
Wow.
So this denominator now will become s plus 2 zeta omega n squared plus omega d squared. This I call equation 4. I need to factorize this further because why am I doing all this? Because I'm trying to get to a form so that I can do inverse Laplace. So far, I still could not. If you look at your Laplace table, there isn't a form that looks like this, but close enough. So what I need to do further is to factorize it more. This numerator, s plus 2 zeta omega n, I can break it down. S plus zeta omega n plus zeta omega n in the following way. Right? So that numerator, if you add them together, you get 2 zeta omega n. And this denominator would be the same on those two terms. S plus zeta omega n squared plus omega d squared. This term here, I'm going to keep it because it looks like now I could do an inverse Laplace for this. Right? Later on, I'll show you. So this term, I'm going to keep. This term over here, I still could not do an inverse Laplace according to the Laplace tables. So what I'm going to do is to factorize it a little bit more. What I'm going to do is that I'm going to break this into two terms that I multiply together. So this denominator plus omega d squared is going to stay. This numerator over here, I'm going to bring this zeta omega n over here. And then have the omega d up there, omega d down there. So that I've not done anything like adding a new term to it. So now we can do the factorization. Sorry, now we can do the inverse Laplace. Inverse Laplace. So I want you to see this form over here. Does it correspond to any form that you find over here? This is kind of like A, right? S plus A over bracket S plus A squared plus omega squared. Correct? This form. So I'm going to use this form. Now we're able to do an inverse Laplace and we'll get this form over here. Where this A now will be omega zeta omega n, and this omega there will become omega d. So I'm going to write that down. This term that's over here, can you see another similar form? Which one? This form here, where this one is omega d, and that one is your zeta omega n. Right? So if I do inverse Laplace of that, then I get this form. So I'm going to write down those two inverse Laplace for me. So after inverse Laplace transform, you have xt. That is from xs in the s domain into the time domain now is equal to x naught e minus zeta omega n t cosine omega d t plus this term that would stay zeta omega n over omega d. And after inverse Laplaceing this, e minus zeta omega n t sine omega dt. This is your time response. So how we came to this, because we had that second order differential equation, and this is a case where we have the underdamped, that is zeta, that's less than 1. This is in your data book, so you do not need to memorize this. Right? It's already in your data sheet. But your data sheet expresses this in a slightly different way, just this part. You have zeta omega n. This omega d, we seen before, is omega n square root 1 minus zeta squared. So omega n and omega n can be cancelled. So you have zeta over square root 1 minus zeta squared. This is a form that's provided in your data book, right? Not this one, but this one. Okay, so just focusing on this. So if I were to sketch this equation of x t, that's your y-axis, against time. So as we increase the time, you can see that there's time here, there's a time here, and there's a time here. If I were to do a sketch of this, how does it look like? It's going to look like this. And go on forever. So this looks familiar, because if you remember, we have this spring, and then I drop it, and then after a while you would know that you will come to a final stop. So that is exactly that kind of motion that you can expect. Okay, that's the equation, xt. This is your equation, xt, and this is a formula that you don't have to memorize this formula. It is provided in your data sheet. There are a few insights. Before I forget, this one is called your underdamped system. Right? This equation xt, this expression here, is your underdamped system. Underdamped system. So there are a few insights. Note the sine and cosine terms. Sine and cosine terms. They are oscillatory. What do I mean by that? The fact that there's a sine and cosine term means that the motion is oscillatory. Because if you sketch sine graph, it's just oscillating. The cosine graph is also oscillating. So that sine and cosine term inside this expression means that they are oscillatory. The other insight, if I were to take this common factor, e to the power of minus zeta omega n t, right? This is a common factor. Put it outside, x naught e to the power of minus zeta omega n t. This term here is your amplitude, and it decreases exponentially. Right? So this term, because it's minus e to the power of minus, it means that it decreases exponentially. Where is that exponential decrease? It's over here and over here. So later on, I'll talk more about these two dotted lines. So there's something that I want to do to give you a little bit more insight. This oscillation is oscillating with respect to this value, right? So it will decay to this value. So I want to find out what is this final value. That final value can be found by using the mathematical technique, that is final value theorem, or FVT. Don't worry if you don't know what's a final value theorem. I'm supposed to teach you, right? So the essence of it means if I take limits of xt as t approaches infinity, this is equal to taking limits as x approaches 0 for the S domain. You'll be kind of like wondering, what is this? I've never seen this kind of thing before. Don't worry, just sit over there and I'll tell you what it is. What I want is that this xt, right, which is this line over here, I want to find out when t becomes infinity, what would be that value, that final value. That's what it means. That's in the time domain. Correspondingly, in the S domain, it's going to be in this form. Why is it in this form? That's because somebody found it out. It's in that form. But how can I make use of that form? That's more important. What I want is to use equation 4. So if you look at equation 4, and then multiply by S. Yeah, small letter s. Take equation 4 multiplied by s. So I want to get s, x, s. So if I were to do that, then I'll have that s plus 2 zeta omega n over s plus zeta omega n squared plus omega d squared multiplied by s, because I multiply it by s over here. Why do I need to multiply by s? Because I want to get to this form. So if I were to take limits as t tends to infinity for xt, what that means is that what I want is x when time is equal to infinity. Yeah. So if x is when time is equal to infinity, that means this oscillation will come to a point where it rests. What is that final value? I can find it from this. If I take limits as s tends to 0 for this entire expression, right? If I take limits as s tends to 0, so let's have a look at the numerator. This s over here is 0, and plus 2 zeta omega n. That s there will tend to 0, so that numerator will become 0. Right? So 0 over whatever is down there will be equal to 0. So it's equal to 0. So what that means is that when time goes to infinity, that value is 0. That's what it means. What is that final value? So there will be other cases that we'll have that when time tends to 0, it's not a 0 value. Right? Later on, we'll have a look at those cases in other language. But for this case, it will be 10 to 0. So there are a few properties that I can list down for this graph over here. This dotted line that's at the bottom, it has the equation that's minus x naught e to the power minus zeta omega n t. That dotted line that's at the top, x naught e to the power minus zeta omega n t. In this graph, there's a certain period. The period is defined from, if you start over here, you go through one oscillation and come back to the same peak. So this time over here, time taken, I call it my tau d instead of tau n. And the formula for that is 2 pi divided by omega d. So all this time taken, they are all tau d. Although I didn't draw the scale, all this will be tau d. So there are a few insights that I want to share with you. No. Theoretically, if t tends to infinity, your x infinity will be equal to 0. However, practically, t is actually finite before x achieves steady state. So we wouldn't need to wait until time is equal to infinity. There will be certain finite amount of time where we consider the system is more or less has came to a rest. So in reality, it's actually a finite amount of time. The other insight, if you notice, after we have added the damping, it actually reduces the natural frequency from omega n to omega d. Why it does that? Why would it reduce? Because your damper absorbs the energy. That's the job of the damper. And where does the absorbed energy goes to? It releases as heat in the damper. And because of this absorption, it reduces your oscillation amplitude. Right, so each of the hump, as it goes along, that amplitude will be reduced and reduced and reduced. Now what that means is that for zeta that's less than 1, is for the case of underdamped, your omega d is less than omega n. So what I have here is the same spring. These two springs are actually the same. And one of them I put a damper, so the other one is only the spring here. So if I were to release them, you'll be able to find that both sides they will oscillate. But then what I'm trying to show over here is that one of the frequencies are actually lower, and the other one, as it oscillates, the frequency is higher. That's what I want to show. So which one is higher, which one is lower? Over there is saying that the one with the damper, the frequency of oscillation is lower. What that means is that when this would be dropped down, if it's at a high frequency, this is high frequency. If it's at a low frequency, then you find that you'll oscillate slowly. So what I want you to see is this too. If I were to drop down, this one's supposed to be at a
oscillate at a higher frequency and this one at a lower frequency. Let's see. Yeah. This at a higher frequency, right? That one's at a lower frequency. So the amount of damping, this damping causes the oscillation to decrease its frequency. And there'll be a time that we'll be doing a lab session. And then during the lab session, you'll be able to understand why natural frequency is oscillating at a higher frequency. And